Lesson 2-4, Tension, Hooke's Law, and Equilibrium. Hooke's Law is for springs or other things that can deform. And it talks about the forces that do the deforming or changing shape. For small deformations, and this means that there's no permanent change, it goes back to the way it was before, the force is linear with the amount of deformation. So spring force equals Kx. K is the spring constant and is unique to each spring. And the delta x is the change in distance, change in displacement, that the spring is stretched or compressed. And since it's linear, the amount of change is the same, no matter how much it's stretched, as long as we're still in the small deformations. And that means that Hooke's law is the reason we can use a spring scale to measure force. Tension is a pulling force from a rope, a chain, etc. But it's only pulling. You can't really push with a rope or a chain. Remember, everywhere a rope connects to something, there's an identical tension. And so let's say we have a bucket here and a rope goes up and over a pulley and down to a person pulling it. So we'll have a tension force pulling the bucket up, and the person is pulling with a tension force there at the same size. Now, if a person is pulling on the rope, then the rope is actually pulling on the person. So the tension is actually going to be pulling on the person. Or if we have a rope going up over a pulley and it's attached to the same box, we'd have two tension forces up because it's the same rope and they're both attached to the box. They're both pulling up with the same force. Equilibrium is when there's no acceleration. When that is the case, our main formula is our net force equals mass times acceleration. But if there's no acceleration, that means our net force has to equal 0. The helicopter in the drawing is moving horizontally to the right at a constant velocity. The weight of the helicopter is 53,800 newtons. The lift force is generated by a rotating blade that makes the angle of 21 degrees with respect to the vertical. What is the magnitude of the lifting force? Well, first of all, my diagram, for the forces for a free body diagram, we shouldn't have the velocity in our free body diagram. We should only have forces. And since the lifting force is at an angle, we're going to have to split it into two components. The vertical is adjacent to the angle, so that would be cosine. And the opposite is the horizontal component, so that would be sine. Now I want the lift force. I don't know R, the resistive force. So I think I'm going to work in the y direction. So my y forces, my vertical forces, would be the lift force, cosine of 21. That's my vertical component. And then I have the weight down. The weight is 53,800 newtons. It says, though, constant velocity. Constant velocity means we're in equilibrium, that our acceleration is 0. So add the 53,800, so it goes on the other side. And then it's L times cosine of 21. So we'll divide by cosine of 21, and we should get about 57,600 newtons. A stoplight is suspended by 2 cables over a street. Weight of the light is 110 newtons. The cables make 122-degree angle with each side of the light. Find the tension in each cable. Well, our light has weight and it has our tensions, where it's 122 degrees on each side. We probably, though, only want our angle from either horizontal or vertical, but it should be less than 90. So if this is 90 degrees, to get 122, this other angle must be 32 degrees. I'm going to start by working in the x direction. In the x, I have T1 going to the left, and it's adjacent to my angle, so cosine of 32. Then I have T2 going to the right. It's also adjacent to the angle, so cosine of 32. And we have no acceleration because it is just suspended there. It's not going anywhere. Add the T1 cosine of 32 to the other side, divide by the cosine of 32, and we get that our two tensions are the same. So now if I work in the y, in the y direction I have T1 sine 32, that's this vertical component. And then, I also have T2 sine of 32 going up, and then the weight is going down. And there's no acceleration because it is suspended. Remember, T1 and T2 are the same, so I really have 2 T1 sine of 32 minus my weight, but the weight is 110. Add the 110 to the other side, and divide by 2 times sine of 32. So 110 divided by 2 times sine of 32 is about 103.789, so about 104 newtons. And T2 is the same thing. A mountain climber in the process of crossing between 2 cliffs by a rope pauses to rest. She weighs 535 newtons, so we'd have some weight of 535 newtons. Find the tensions in the rope to the left and to the right. So here's a tension. What if I call that tension 1? And here's a tension. What if I call that tension 2? Now, these are measured from the vertical, so this angle would be the same because alternate interior angles are congruent. So if I draw right triangles, and what if I work in the x first? If I work in the x and go F net equals MA, I'd have T1 going to the left. It's opposite the angle, so it'd be sine of 65. T2 is going to the right. It's opposite the angle, so it'd be sine. And there's no acceleration because we're pausing. We're resting. Let's add the T1 sine 65 to the other side. And then divide by the sine of 80. So T2 is 0.9203 times T1. If I work in the y, net force equals mass times acceleration. In the y, I have the vertical component of T1, so it'll be T1 cosine of 65 because the vertical component here is adjacent to the angle. And T2 cosine of 80. And then the weight going down. And there's no acceleration. Cosine of 65 is 4226. T2 is 0.9203 times T1, and cosine of 80 is 0.1736. So I'm going to multiply these two and add it to the 0.4226. And I get 0.5824 T1s. I'm going to add the 535 to the other side. So divide, and I get that T1 is about 919 newtons. T2 is 0.9203 times T1, so T2 is about 845 newtons. So when we're at different angles, the tensions are different. The previous problem with the stoplight, the angles were the same and the tensions were the same. But different angles, different tensions. A 10-gram toy plastic bunny is connected to its base by a spring. The spring is compressed in a suction cup on the bunny holds it to the base so the bunny doesn't move. The spring is compressed by 3 centimeters and has a constant of that. How much force must the suction cup provide? What forces are there? Well, the spring is pushing it up, and the suction cup is pulling it down along with the force of gravity, known as weight. There's a normal force between the bottom and the table, but we don't want that. We want between the suction cup and the base. And yes, there is a normal force there, but we want the point where it's just ready to break free, so the normal force will essentially be 0. So net force equals mass times acceleration. I've got the spring force up, the weight down, and the force of the cup down. And there's no acceleration yet. Spring force is K delta X. Our weight is mg. And we're looking for the force of the cup. So it says the K is 330 newtons per meter, and we're compressing 3 centimeters. Well, that needs to be converted. There's 100 centimeters in a meter, so it'll be 0.03 meters. Our mass is 10 grams. There's 1,000 grams in a kilogram, so it'll be 0.010 kilograms. And I'm going to add the force of the cup to the other side since that's what I'm solving for. So this is 9.9 newtons. This is 0.098 newtons. So if I subtract those, I get 9.8 newtons that the cup needs to apply.